Hi everyone, and welcome to our weekly AATRN seminar. The speaker today is Radmila Sazdanovic, and she will tell us about the shape of relations, knots, and other stories.
Thank you, Sarah, and thank you everyone for joining. It's an absolute pleasure and joy and honor to be here and share this story with you. There's many reasons why I'm super excited about this project, why I love it very much, but one of them being that it actually ties in my background in knot theory with my interest in topological data analysis. And it's kind of a little bit of a full circle, right? Because both of these are branches of topology, right? And then they sort of come together in a beautiful way. And they also illustrate a way that sort of TDA can be used in theoretical mathematics. Okay, so again, the title is The Shape of Relations, Knots and Other Stories. There's going to be very few of other stories. But I do want to emphasize that all of the techniques developed in this talk are applicable to sort of other data sets and other settings. So what I would like to do here is sort of showcase how some big data techniques can be used in theoretical math. So I'm going to introduce some new or at least novel tools from applied algebraic topology and then compare with other tools. Again, the main focus will be on knot theory, but the tools are not limited to knots or theoretical mathematics. And in particular, knots provide a data set that's infinite, but we can't reach, and we actually don't know how to sample. So if you have, or if you're interested in data sets where representative sampling is at least impractical, maybe this is a good talk to pay attention to. Again, the focus on knot theory is going to be mostly for analyzing knot invariants and the relations between them, hence the shape of relations. Okay, so I'm going to start with just a brief intro. So you don't have to know any knot theory. Again, use these data that's going to appear as just an example. But if you are fond of knots and knot theory, then again, maybe there's going to be some domain-specific results that are going to be interesting and exciting. So a knot is just an embedding of S1 in R3 up to ambient isotopy, which means that you can have a piece of string, you can embed it in R3, you can stretch it, you can bend it, but the strands cannot pass through each other. And knots appear in many applications, DNA, RNA structures. There were a while ago a promising structure for setting up states for quantum computers. They also appear as dislocations in liquid crystals. So basically where the particles have preferred directions and where those directions don't match, they actually appear to be 3D structures, and they can also appear in light. Recently, there's been a lot of interesting work that focuses on elastic knots, which are basically global minimizers of certain type of energy. It's called the bending energy. And these have lots of applications. And then the idea is that if you are within any particular topological knot type, where you sort of don't care about embedding, like you can stretch, you can bend, you can make it bigger, that's kind of a more general story than the one that's needed for the elastic knots, because they actually are made out of certain materials and they satisfy some physical laws and have actual physical properties. So again, I'm going to go back to this at the very end of the talk. Okay, so what about knots? So again, people who do knot theory usually like to be able to distinguish knots. And that's not easy just from looking at their embeddings in R3. So we have developed knot invariants, and the knot invariant is a function on knots, and it has to be kind of respecting the topological knot types. So basically, if you have two different embeddings of the same knot, you want your function to attain the same value independent on how that knot is presented. So again, the words for these are the functions, the knot invariants are those specific functions of knots which attain the same value on isotopic knots that are considered equivalent, but most of them can fail to distinguish knots that should be distinguished. So they might assign the same value to different knot. So I guess that's can be thought of as noise or as a loss of information, right? And then they have many different shapes, right? So they can be numerical, like a number of components, number of crossings. They can be polynomial, and some of the ones that we're going to be talking about now, again, I won't go into any details of them, but they're like Alexander, Jones, or Kaufman polynomials. They can be one variable or two variable polynomials. What's very special about them that they actually have integral coefficients. And then they can be algebraically more sophisticated. They can be groups, for example, the group of colorings or the knot group. That's a fundamental group of the knot complement. You take R3 or S3, you take the knot out, you do your standard homology. That's what knot group is. But again, the thing here is that there's more than 15 variants, but most of them are either incomplete, so they fail to distinguish some knots, or if they're complete, and even if they're not complete, they can have very high computational complexity. So they can be hard to compute, but then even if you can compute them, they may be hard to compare. So for example, if you have two groups, comparing different group presentations is an NP hard problem, so it won't help us much. But knot invariants are used to distinguish knots, and the way that that's done is basically you give me two knots, I try my favorite invariants. Usually, if knots are very complicated, I'll start with polynomial time computable ones. If I get different values of the, let's say, Alexander polynomial, we're good, knots are different. If not, I go on to the next invariant, the next. Okay. So what I would like to know is how to compare knot invariants. What are their discriminative powers? And if you give me two knots, which invariant should I choose if I know something more about the types of knots you're giving me? So this, I guess for this crowd, I think the analogous question in TDA could take the following kind of form. Sort of if you have certain type of data and you know some things about it, then you need to be smart about choosing the topological summary that you're going to use. Like which TDA tool would actually give you the results you need. So this is kind of the analogous question on knot theory side. If I want to distinguish certain types of knots, which algebraic or numerical summaries can I use to distinguish them? And then the basic question is, well, does it distinguish just the plain circle with no crossings, like the invariants that we have? And even this is a very hard question from the theoretical point of view. And it's known that some, like genus or knot floor homology or Jovano homology, can distinguish the unknot. No other knot has the same value of these invariants as the unknot, but it's still open for the Jones polynomial that's been constructed in 1984 and led to Fields medal. So here's a sample of incomplete list of papers that have all been devoted to answering the question of which knots can be distinguished by Jovano homology. Basically, if you give me a knot, and does it have a unique Jovanov homology like this, so that no other knot has the same Jovanov homology as this one? And again, this is a long list on more than 1 decade, and I've contributed to it. So it's a paper and a theorem that has like 5 authors. And it basically says that Jovano homology detects one particular very simple 4-crossing knot. And it involves a number of spectral sequences and very sophisticated theoretical arguments for just one knot. So to me, or anyone who sort of does any sort of data analysis, this sort of says, well, if we can get data and we have enough samples, then we could use some of the big data techniques, right? And this was my motivation, right? And but just before I get there, there's some things that we can say kind of back to about just comparing knot invariants theoretically. So everything that's highlighted in blue here, those are like knot polynomials. And then everything that's kind of related to a particular polynomial that's shaded light green, it's a categorification, it's a homology theory. So for example, we know that the categorifications, the homology theories are better invariants. They're strictly stronger distinguishing knots than the polynomials. And then this Hom-Flapitti polynomial is a two-variable polynomial that actually specializes, that's what these arrows mean, to these one-variable polynomials. So we know that it should be stronger than all these polynomials, and it is. But then there's theoretical results that sort of say that Hom-Flapitti polynomial is not better at distinguishing certain tree braids than let's say the Jones polynomial. So these are the types of questions that I would like to sort of understand. And it can also happen that the polynomial invariant like the Jones polynomial together with another numerical invariant, it's called signature, actually completely determine Hovanov homology of a large class of knots and links that are called alternating knots and links. So basically, you know, what can we do and how can we do it considering taking into account the computational complexity of all of these things and the time needed to compute them and effort. Okay, so back to the thing. We know a little bit theoretically, we would like to know more. And indeed, big data techniques are like a good tool because knots are big data. That actually has been a theorem since 1987. It's a theorem of Ernst and Summers that says that the number of distinct knots grows exponentially with the crossing number. And again, this is the state of art currently, or maybe as of a year ago, where we sort of say that if you go up in crossing number, up to 17 crossings, we have 1.7 million, but for 19 crossings, we actually have 350 million knots, different knots, and those are only prime knots. But again, data is there, starting with the Rolfson table of knots up to 12 crossings, and then going all the way to Burton's result, and then again, Hosted this over the weeks. But then the question is like, how do we turn these knots in the data? How do we create a representative sample of these knots? How do we ensure that the conclusions we draw from this data are stable with respect to kind of sampling thing? And again, I won't justify it now because it's irrelevant, but like we don't know how to sample not data. And one thing that we've sort of encountered is that the results that we obtained were sensitive to the choice of encoding. But what I'm going to talk about now is one particular way we encoded things that actually gave us really good results and was actually stable. So how do we construct point clouds from these invariants? So I'm going to pick an invariant, let's say a polynomial invariant, so maybe Jones or Alexander. And my input is going to be the coefficients of these polynomials. As I said,
sorry, Radmila, we have a question. What is Rolfson table?
Rolfson table. So what I wanted to emphasize here is that over the, I guess, last 50 plus years, many mathematicians have devoted a lot of time to tabulating knots and actually distinguishing them. And one of the first and go-to tables is a Rolfson table compiled by Dave Rolfson at the very end of his book that contains all knots, different knots up to 12 crossings. And then Hosted in weeks had the first 1.7 something knots up to 17 crossings. And then for everything that's higher, crossing number 18, 19, and 20, there's databases online. So I'm just sort of citing these as sources of different knots that sort of we can use as a basis to kind of produce these point clouds. Does that answer the question?
So I apologize.
Oh, thank you, Erin.
Question is, all the tabulated knots are prime or not? I guess that's sort of the question. If
okay,
are they not?
So I've actually opened the chat. I don't know why I did not do it before. So the knots that I'm working with are prime knots. The situation is a little bit more dicey with composite knots, like connect some of things. So in this talk, I'm going to be focusing only on prime knots. That was an excellent question. Thank you. Okay, I have a chat open now, so feel free to type it in, but also respect whatever rules Sarah gave you. Okay, so basically we're turning the coefficients of these one variable polynomials into vectors. And you know, what do? We need to sort of find what's the minimal, what's the maximal power, so that we can sort of see how big our point cloud is. And then we're going to center everything at the free term and pad everything by zeros. So I think it's much easier to explain this just by a sample. So again, what you see here, 0, 1, 3, 1, 4, 1, 5, 1, all the way to 6, 3, those are all 6 crossing nodes from Rolfson tables, or at least their notation. And then J just represents the Jones polynomial. And for example, this top row is telling me that the Jones polynomial for the unknot in this normalization is just 1. And then for the 3, 1 knot, that's called the trefoil, it's Q to the power 3 minus 1 to the minus Q to the power 4th. Okay. So this is for the Jones polynomial, and I've just included here just sample vectors for other type of knot invariants. So again, Alexander is also one variable polynomial. It's a Laurent polynomial that's symmetric. So this is how so for the unknot, they're all equal to 1. And then for the trefoil, there's like more variety. Homefly PT is a 2-variable polynomial. So we just treat it as a matrix that we flatten into a one long vector, which is not the most natural thing and probably the right thing to do. So if you have any ideas, please do let me know. That's true both for Khovanov polynomial and the Homefly PT. And then what I want to point out here is, again, I've shown you how many knots we have for each one of these types of crossings. And then I want to emphasize how big dimension-wise these point clouds are. So for 17 crossing nodes, Alexander polynomial is actually 17-dimensional. Jones polynomial has 51 dimensions. Homefly PT 152, and Khovanov again. So let's sort of say 1.7 million knots and 1.7K dimensions, roughly. So I hope that qualifies as big data, and it definitely comes from theoretical mathematics. So it should be at least noise-free. So what are we going to do? So I want to use topological data analysis tools. And then again, there's kind of 2 big streams. One is persistence and the other one is mapper. So I'm actually going to use both in this talk. So the first one is going to be what we call persistent PCA. That's a joint work with Mustafa Hajij and Jesse Levitt. It's about 5, 6 years old, 6, something like that. And what we did there, we sort of said, okay, these types of this type of data is hard to sample, right? But we sort of know tables are organized by the crossing number, and we can sort of think about other filtrations that one could use. So we could try to kind of get away with not being able to find a representative sample by employing the persistence and sort of requiring that whichever results we obtain using TDA tools, they persist through our filtration. So this is actually how we defined in the paper the dimensionality of the point cloud. We sort of said that D is the smallest value for which the normalized explained variance of the first D principal component is more than 95. Again, 95 was arbitrary. And then we require this to be stable as we're going through the crossing filtration from 12 to 13 to 14, 15, 16, and so on, number of crossings. So I'm just going to give you sample results. For the Jones polynomial, it turns out that it's 3-dimensional or possibly slowly growing. And what you see here is not so 3-dimensional looking, but definitely 3-dimensional projection, where you could sort of see these slices that are colored actually by a different numerical non-invariant called signature. So you can sort of see that this 3-dimensional, like the big features, these sort of like flares, can actually be differentiated using signature, right? So different colors represent different values of signature. Okay, and then if you look, again, I'm not going to go into these details here, but we sort of did analyze these filtrations. And if you look at the explained variance for the Jones polynomial, the good news is actually, again, if you want to look at one thing, it's good to look at this bottom right picture. And this one says that the more significant principal component is, the more stable it is across the filtration. So you could have seen that, I don't know, PCA number 5 kind of goes up and down, and we actually understand why it goes up and down. And I'm looking at Adam in the audience, right, between odd and even. But again, the first and the second, they're sort of more stable. Then if you look at the persistent PCA for the Alexander polynomial, it actually is one-dimensional. It's completely explained by just like one principal component. And again, you can sort of see the coloring by signature that sort of doesn't look like anything is explained here. And then kind of speaking of trying to address a little bit the sampling issues, we actually looked at the data that had very few knots, about 5,000 knots. And they all come from the same family of so-called torus knots. Again, don't worry if you don't know what they are. But what's good about them is that we have formulas for their polynomials, so we can actually compute them for really high crossing numbers. So here, again, we're kind of trading the number of knots. So we have more than 500,000 or like almost 2 million or 10 million in the other samples. Here we have only about 5,000 knots, but they go up really high in crossing number, up to 2,000. And this actually kind of doesn't look good. I mean, again, this is what PCA gives you. The starting dimension is 3,000, and it actually kind of falls very slowly. Again, I would encourage you to look at the details. There's sort of some ideas of how the sampling works, and this sort of shows the data is actually really finicky, and we should be very careful about how we're dealing with it. And now I want to actually talk about the different venue or the different tool that's based on a mapper. And again, I'm just going to quickly do the overview of the mapper, just so that we can introduce ball mapper and extensions of it. So how does the mapper work, right? So input, it's motivated by the Reeb graph. So if you input is a manifold M and some height function F, in this case, I have a torus, right? And the height function that's indicated with the red graph. I can define an equivalence relation that sort of says that the 2 points, X and Y on M, are going to be equivalent or merge into one if the value that that F achieves on these 2 points is equal and they belong to the same connected component. So again, all these points on this circle are going to become 1 point here on the right, because this is one circle, it's one connected component. But if you look at this level here, there's actually 2 circles, so we're going to have this branching, and then they're going to merge again, and so on. So Reeb graph is just the quotient space of our manifold with this relation. And again, this is the intuition and the motivation for the mapper. You have some point cloud, you have some height function, and then you need to make choices, right? So the input is the data, the length or the height function, and then the overlapping cover of R. And then the mapper graph can be thought as the nerve pullback of the cover R back to the X. So again, this is what I've illustrated here with the length from before. We get these sort of components. Because the things overlap, we're going to connect 5 to 4, here 7 to 8. This is the graph that we get. And we can additionally color. If we are given some sort of function, we can do extra coloring. So basically, mapper is a combination of dimension reduction, clustering, and graph network techniques to try to give us a better understanding of our data. So what I'm going to use here instead is Pavel Dlotko's version of a mapper algorithm. It's called ball mapper. It was introduced in 2019. And its simplicity spoke to me. And I know that not making a choice is making a choice, but basically, the idea is that the ball mapper algorithm has only one single parameter. As an input, we use a point cloud and a single parameter. That's the radius of the ball. And then step 1 is sort of to collect, to choose the collection of points, so-called landmarks, using the epsilon net construction on the point cloud. And the idea is that this collection of points needs to give us a cover of our point cloud subject to this epsilon radius. So in step number 2, we basically look at this cover that's a collection of balls centered at these landmark points. And we construct a graph that's called a ball mapper graph in the same way as we would do it in the mapper construction. Okay, so I promised the shape of relations. So this is now a joint work with Pavel Dlotko and David Gurnari. The paper is called Mapper Type Algorithms for Complex Data and Relations, and it's available on the archive. And basically the idea, the paper started with me bothering Pavel with the knot data, right? The idea is that when you look at knot data, it's hard to sample, but we know that it has symmetries. So what we did, we developed a way to incorporate symmetries in the ball mapper algorithm. So that's going to be one of the things. I want to analyze the relations between my knot invariants. So we developed a tool called Mapping Mapper that's for that, for analyzing relations or functions between very high dimensional data sets. And again, it can be knot invariants, can be just different descriptors of any given object that you're interested in. So maybe it's certain materials, maybe it's like a superconductor, and then you have one data set that sort of describes superconducting properties, the other one that's just the chemical structure of it. Or maybe cancer patients, which is actually the illustration on the bottom. And then last but not least, we're actually going to combine the functionality of both mapper and ball mapper algorithms to sort of try to address the issue of the dimension of the lens function, right, which is usually just x to the real numbers, and we would like to sort of be able to do it with a higher dimensional with r to the n with n higher, so that there's hopefully not as much loss of information. Okay, so how are we going to do it? So I'm going to illustrate all of our algorithms on the knot data. So in particular here, I'm going to focus on either Jones or Alexander or Homefly PT data. But again, it just means that I have different descriptors for an object of interest that's a knot. So again, you can think about it in this term. The fact that they're not is completely irrelevant. So first, I want to sort of say, again, our goal was to get stable results because we know that we don't have a representative sample. So what you see on the top row is, again, how Jones ball mapper changes when we go from 15 to 16 to 17 crossing knots. And again, this data grows exponentially, so we know that going between 15 and 16 crossing knots dominate the whole distribution. And then the standard thing that one needs to check, of course, is stability with respect to the parameter that we are like putting in to our algorithm. So the epsilon, the radius. So what you see in the bottom on the bottom row is sort of zooming in. So if we fix the number of crossings, so it's 17 crossing data, about just under 2 million knots. These are the structures that we sort of get for epsilon equals to 50, 100, 200, and sort of exhibits the stability. And then, again, the feature of both mapper and ball mapper is that we can color our clusters based on some other values that we have. So again, this is going to be more interesting to people who are already into knot theory. But what I have here is Jones ball mapper that's colored. Each cluster is colored by the average value of the determinant. Here we are sort of having a binary property. So what this picture here is telling me is that in the central regions of these ball mapper graph, I have a mixture of alternating and non-alternating knots where when I move along away from the center along the flares, I get only alternating knots, and actually for that matter, the highest crossing alternating knots. And then back to the signature again, here, similar to what we had in the persistent PCA, we sort of can see some sort of flare-like structures that are monochromatic when it comes to signature. And then a hint to what's coming next, we can notice that although mapper graphs are abstract graphs with no particular embedding, we can sort of find an embedding where you can sort of stretch out the flares that have the signature is always even, but we can split it into the combination of flares that have signature mod 2 equal to 0 on one side and mod 4 equal to 2 on the other side. Okay, and again, these graphs sort of naturally, that doesn't look two-dimensional at all. It sort of fits in 3D. But when we look at the Alexander data, again, the same thing, the same coloring functions. We actually see this sort of linear structure. And we can sort of see that the determinant grows from the middle outwards. The mixture of non-alternating knots in the center, alternating knots at the end of the two big flares that we have. Signature not very informative, but signature mod 4 again shows this dichotomy, right? Where we have one flare with 2 mod 4, 0 mod 4 on the other side. Okay, so what do we get? So first, I promised that we can visualize symmetries, or at least incorporate symmetries. So equivariant ball mapper extension is just for that. If you have a point cloud in some metric space with some finite group acting on it, or you sort of just know that it exhibits some symmetry, we can leave the action of that finite subgroup to the ball mapper graph by, deciding that if we pick a point from a point cloud to be a landmark, we include the whole orbit of that point in our collection of landmarks. And that sort of would give us a ball mapper with the induced symmetries. So again, for specialists in knot theory, if you look at the knot and its mirror, which just means that you change the crossing from this one to the opposite one, you sort of know that the Alexander of a mirror knot is the same as the Alexander of the mirror, but the Jones polynomial actually satisfies this relation where you replace the variable q by the q inverse. And sort of similar with signature. The signature of a mirror knot has actually the opposite sign to this one. So on the left side here, you see ball mapper. That's just the standard ball mapper. And on the right-hand side, you sort of see the equivariant one. So I think the pictures illustrate the algorithm and speak for themselves. The next thing that I want to do is maybe the heart of the talk and one of the most interesting things. So an extension that we developed, it's called mapping mappers, sort of says, okay, mapper is a tool that builds a model of a space X with some function on it. So what I want to do is I want to be able to compare these structures, which is kind of equivalent to maybe comparing the descriptors or finding some dependence between these two sets of descriptors, or maybe correlations. Anyways, so what you see here on the bottom picture is comparing the custom colored Alexander ball mapper, where I sort of picked these clusters because we were interested in them, and then we sort of see where are they located within the Jones ball mapper. So how does this work in general? Again, there's like a lot of words here. But basically for mapping mappers, we actually have 2 point clouds, both in really high dimensional, embedded in really high dimensional R. And then we have some relation between them. I'm denoting it by F. It could be a function, right? But it doesn't need to. So what we're going to do, we're going to construct the ball mapper graph of one point cloud and the ball mapper of the other point cloud. And then we say, well, but we have this relation or a function. We can use this function to actually define a map between the vertices of the ball mapper graphs. Sorry, that maps a vertex in the ball mapper graph of X and gives us a coloring function on the ball mapper of Y. That's the idea. So again, going back here, I chose certain clusters here on the left. This is my X. And for each choice here, I'm actually going to get the coloring function on the ball mapper of Y. So how do we color? We basically say, well, okay, each cluster in the ball mapper of Y will be colored depending on how many points from the chosen cluster in X are being mapped to that particular one, and then scaled by the size of the cluster. So it's basically the percentage of points in this W that are in the image of the points covered by the vertex in the ball mapper of the original one. So again, the output here is the coloring function, and you can get one for each vertex in the ball mapper graph of X. And this is what actually this approach gave us. I'm going to illustrate with several results. So first, based on some experiments, we sort of noticed that this rainbow linear coloring of the linear structure of the Alexander polynomial actually nicely lends itself to coloring the Jones-Ball mapper graph. But what this really tells you is that some sort of shadow of the correspondence of the data in 17 dimensions with the point cloud in 51 dimensions. So it's like really visualizing a dimension or a relation between high dimensional point clouds. But it's also very exciting because it gives us the explanation for the persistent PCA, right? So first of all, notice that there's a similarity between the results that we've obtained using PCA, where Alexander polynomial was one-dimensional, and the Jones polynomial 3 or maybe 4, slowly growing. But now, using mapping mappers, we've actually managed to sort of see that one dimension, the principal component of the Alexander polynomial, is actually shared with the Jones polynomial. So it can be sort of mapped onto the three-dimensional structure of the ball mapper. And later you're going to see that actually this is what the determinant is, which is actually a specialization of both of these polynomials. What I want to show here is actually ball mappers for the Jones, Home-Fly PT, and Hovanov polynomials. Actually, notice that Home-Fly PT and Hovanov are two-dimensional, two-variable polynomials. And if I was just, again, for the lack of better measure, if you just looked at them, they all look like star-like graphs to me. Okay. And this could be very deceiving, right? Because you could sort of jump to the conclusions that it's the same structure. But what mapping mappers actually allows you to do is to kind of do a more in-depth analysis. So what I'm illustrating here is that if you pick this gigantic cluster, which I hope you can see here in the middle of the Jones ball mapper, it maps to the central collection of clusters in the Hovanov homology that clearly seem more distinguished, right? More delineated, which is good. So it's kind of like maybe scaled, but if you actually pull it back to the Home-Fly PT, which again is not surprising to non-theorists, but then it gets sort of spread throughout the whole flare. So it sort of says that the distributions of knots here are like very, very, very different. And again, that could be used as a hint to which things are going to be distinguishable by one and not the other. But again, we were able to detect and analyze the differences between the distributions in these star-like ball mapper graphs. And then just for fun, there's a spectral sequence between Hovanov and here floor homology. So now what you can do, you can use ball mapper to sort of try to track which things go where and sort of analyze the spectral sequence. And again, the idea here is that database question is kind of simple because it sort of says that there are more unique values of the Hovanov homology than the HFK, or Hovanov polynomial than the HFK, but still sort of there's like differences in how that's reflected on the data side. Okay, last development, everyone, I think, would like to be able to use mapper on very high dimensional data and potentially use it with higher dimensional lens function, right? So if I have a function, again, from X to Y, both in very high dimensional sets, but also the difference between the dimensionality of X and Y is just like really, really big. So then if you wanted to generalize the mapper lenses just from R to some R to the N to be more likely to preserve essential information, that's actually going to come at a huge computational cost, right? So if you want K intervals in each one of the N directions, that gives us K to the N cover elements, not very feasible. So here's a workaround that Pavel and David and I suggested. The construction is called mapper on ball mapper. And the idea is that in this setting, right, where X lives in much higher dimensional space than Y, we can actually construct the mapper on X, but instead of using the standard lens function, we can use this function that's provided to us that goes into Y. But then instead of the overlapping cover, that's a key step in the construction of the mapper algorithm, we actually going to use the ball mapper on Y and then pull it back. So here's an illustration. So let's say that this is my very, very, very high dimensional data set, although it lives in 2D X, and then the map is just collapsing the segments that have the same color into one, right? So I go from 6 flares to 3 flares. So what does a mapper on ball mapper do? It says, okay, I have this map F, I have my point clouds. I'm going to construct a ball mapper on Y, that's shown here. And then I'm going to pull back that ball mapper graph as a cover. I'm going to pull it back to get a covering on X. And then I'm going to use that cover that's adaptive to the function to construct a mapper graph on X. Okay, and here I just wanted to illustrate that, you know, if you're pulling back this cluster, it pulls back to 2. Yellow, again, pulls back to 2, but the central orange cluster actually stays central. So there's a fiber type thing going on there. So this is how it looks on knots. So again, I have knots here, and I have these different types of polynomials. And as you've seen, some are much higher dimensional than others. So I've actually illustrated the Jones ball mapper, and I've illustrated the Alexander ball mapper. So what I can do, I can construct ball mappers for each one of these, and then I know that Homefly PT polynomial specializes to both of these. So I'm going to focus on this particular specialization and show you what we get. So this is the ball mapper for the Jones polynomial. This is the Homefly PT ball mapper for the same data. When we apply mapper on ball mapper algorithm here, by pulling back from Jones, we actually get this mapper on ball mapper graph that sort of shares some similar structures or features as the Homefly PT ball mapper, but it has these additional flares that are no longer monochromatic in signature, but they are monochromatic in the S invariant. Again, this is just for a specialist. What I'm saying is that it seems that we can get sort of to some additional interesting features of our data using this construction. Okay, so I think I'm reaching the time, but I would like to give you a summary and then maybe just mention some of the things that that we can do, where we can go from here. So again, independent of knot theory, ball mapper provides a way to visualize high dimensional data. Equivariant ball mapper is for data with observed or assumed symmetries. And just to emphasize, this is very challenging / impossible to achieve using just the mapper construction. Mapper on ball mapper, again, it's a hybrid between these two algorithms, and I think it sort of brings up the best in them. And it sort of allows us to at least have a try or a go at having a higher dimensional less function. And then mapping mappers is a tool for comparing data sets or visualizing functions between high dimensional data spaces. Okay, so this is a good stopping point. If there are any questions.
I guess you're started.
Yeah, okay. So what I want to sort of show you is some of the things that
I think there was a question. Was there a question? From Adam or no? Okay.
Yeah, well, maybe I have a question.
Okay.
Hi, Radmila. So when you have a multivariable polynomial, how do you decide the order of the variables in the embedding?
Again, not a good way, just a matrix, and I flatten it into rows A and Z.
Yeah.
If you have a better suggestion, please go ahead. Yes.
Okay, thank you.
You're welcome. Okay, so what I would like to sort of just say is that we actually rediscovered, we did not find new theorems, but we rediscovered an old theorem. So remember that split into ball mapper graphs of both Alexander and Jones, where we sort of have mod 4 equals to 2 on one side, 0 on the other side, mod 4 equals to 2, sorry. And then we have a messy core. So what Davide did he actually used the SVM to sort of try to see whether this messy center persists in 17-dimensional space. And it turns out that just the linear SVM classifier got the perfect separation using +1, -1 vector. That is actually, you know, the vector that sort of corresponds to evaluating the Alexander polynomial at -1. But actually the same approach failed to converge on the Jones polynomial data that's 51-dimensional. But then we knew that the mapping mappers sort of gives us the relation between the mapper on the Alexander and on Jones. So whatever was true on the Alexander should have been true on Jones. So basically what we did is we did rediscover the folklore theorem that sort of says that both the Alexander and the Jones polynomial sort of determine the signature mod 4. Another interesting conjecture is due to Garoufalidis, and it actually says that something that's much stronger than the Jones polynomial, the color Jones polynomial, determines the signature of a knot. Now, again, the Jones polynomial is just one of the color Jones polynomials, and this conjecture is actually true just for a subclass of knots, but we still wanted to sort of examine the relation between the Jones and the signature. And we know if you sort of look at it, but in a sort of statistical way, right? Because we know that the Jones polynomial fails to determine signature miserably. And here's the slide with all of the examples, not all, but some of the examples that show ways in which you can have two knots with the same Jones polynomial, but different signature. But this is what we get. So we sort of, by looking at the ball mapper graphs and using our tools as sort of exploratory tools, we sort of have a hypothesis that sort of says that the Jones polynomial determines the knot signature, provided that it's far away from the center. And as I've hinted before, it seems that the sort of distance from the center is determined by the value of another knot invariant that's called the determinant. In this case, it can be also seen just as a norm of the Jones polynomial, but it's also, you know, has interpretations in terms of higher dimensional sort of ways of looking at knots. So what you see here is a two-dimensional PCA projection of the coefficients of the Jones polynomials on the left, and then the normalized version of it on the right for all alternating knots with 15 crossings and the determinant greater than some number. And you sort of see the perfect separation. So that's something that we would like to prove. And then an interesting fact that when you look at the ways in which Jones can predict the signature, sort of these little stars, so sort of see that the prediction sort of what's the fraction of the knots that can be predicted as the determinant increases. And the sort of, this one says, I forget what's the cutoff. But anyways, the idea is that we have these like jumps based on the parity of the number of crossings, because this is for 12 crossings, 13, and so on. But sort of it sees that you sort of see that it's declining. But what's really interesting is that the predictions are more accurate on non-alternating knots than alternating knots. Again, that's just for the specialist in the audience. Okay, so the good news is that all of these tools have been implemented thanks to Davide, and you can sort of access them either on Zenodo. You can find interactive ball mapper graphs if you're interested in knots on the Dioscuri Center webpage, and otherwise you can go to GitHub or Zenodo. And what Davide also did, he actually visualized one of the databases, sort of that's larger than the Rolfson table. There's but it's based on the Rolfson table of knots. Knot info has all of the crossings and all of the invariants for which we know the values available online, but it's in the form of a table inquiry with like lots of data that, so what we can do is that we can visualize it and sort of like look for interesting statements there. And then what's next? So somehow there's a huge lack of statistical kind of analysis of knots. There's recent work of Adam Lorenz and his collaborators, and then on the sort of geometric side, other people that sort of talk about average values or distributions of values of non-invariants. But again, I claim that sort of this statistical or global nature of these point clouds could provide valuable insights. of course, what's missing here is to extend this analysis to random data and vary the choice of the embedding and the metric. And then maybe we can provide some insights into how useful are these not invariants as not descriptors. One thing that I would really like to do, and I think it's going to be especially interesting in experimental settings, is to kind of relate the algebraic not invariants that I've used here with more geometric not invariants and properties like rope lengths, not energies, etc. And then the global question is, using AI tools or TDA or whatever, which theoretical results can we get or improve? And also, can we sort of like strengthen the relations between topology and AI in the sense of like using TDA tools to sort of illuminate some of the recent and exciting results in not theory and theoretical mathematics that have been achieved using AI techniques. So that's all. I would love to thank my collaborators, some of which might be here, and of course the funding agency and the organizers of these seminars, and all of you for attending. Thank you.
Thank you so much, Radmila. I would ask everyone to unmute themselves so we can give a round of applause. Well, Powell commented that for those of you who don't know, you can get a Nobel Prize not only in physics by doing AI, but also in chemistry, as we learned today. Yeah. Okay, great. So do we have questions for Radmila? Feel free to raise your hand or just unmute yourself.
I have a couple of questions. I can start. I was wondering, with the ball mapper, you need to choose this epsilon parameter, right? How did you sort of lead the search for the optimal epsilon or good enough epsilon in these cases that you considered? Because it's probably also varies between, like, when you consider Jones polynomial and then the other polynomials or the other invariants, the other descriptors.
That's an excellent question, and the one that I did not have to worry about. So I'm thinking that if David is not here, I think Pavel is here. Pavel, would you like to comment?
Yes, so selection of parameter is always difficult. Essentially, there is try and error. We can also look at the connectivity of the graph and use this as a kind of analog of an elbow method in, for instance, k-means. But I'm not aware of any general rule of thumb. So with David and with David is graduating right now, and with Mathis, who is an intern from France, we are actually about to submit a paper when, under assumption that your data are sampled from a manifold, it may be connected or disconnected. If we have a good estimator of geodesic distance on the manifold, then we can kind of tune the epsilon. But it's also very much like the parameter in the persistent homology, or maybe think about it as a resolution of an image. So if you look at, very detailed resolution, you get many connected components. Connected components are small. You get all the fine details. But if you make your pixels very big, just to visualize that thing, you see just the global thing or maybe nothing. So I do not think that the question is well stated. It is really a matter of the trade-off of what you want to see. And, as in data science, you typically do the grid search of parameters to essentially any method to make sure that whatever you see is actually over there. It's not a feature of the specific parameters. And that's precisely what we did. And Radmila actually showed those plots where we vary the epsilon just to make sure that, what we see is not a ghost in the machine.
So Radmila actually carefully chose her background photo, which is also like the last slide that I think illustrates our approaches really well. If I may add, it's not going to be a useful comment, but I think it's the way that I think about it. So you sort of, it's a work of David Vella about a Picasso and Dali painting an egg, right? And they're both useful and beautiful in their own ways. So I think at the moment, the question that you've asked is sort of absolutely essential, right? Because we need to know, and Pavel touched up on it, we need to know what are we getting with the particular choice of a parameter. But also I feel with like all of the tools that are available, I guess the real question is like, once we put, especially if it's in theoretical mathematics, right? Once we put all of these tools together and sort of try to get a theorem or something, then the question, or like prove a conjecture, then the question would be, well, if we can't do it, then even if you can't do it by like 1% or 2%, it's not going to be a theorem. But like, what's hard about how can we reach those 2% or whatever 1%? Like, what makes it like not a theorem? And can we deal with it, or like what makes it hard for all of these tools, or maybe not? You know, I don't know. I'm not answering the question well, but I hope it can be seen as a feature, not a bug.
Yeah, absolutely. And there's also probably like no size fits all, right? And then yeah, then one has to choose one over the other depending on what one searches for, I guess.
But I mean, again, like the question here is that there's no noise, right? But also there's no representative sample. So yeah, and I can actually quickly, okay, but there are other questions, so let me not go there.
No problem. Thank you.
More questions? We're gonna do one more question, like recorded, and then we're gonna take them offline. So if anyone wants to ask, so then I'm gonna ask. So I wanted to sort of like this star shape, was that something you were expecting, or like do you have a good explanation for it, like of how like it came about? Because it's okay.
So actually, you know, this was quite an experience for me, right? So we actually got the, again, it's not a star-like structure, but it has this flare, like I don't even know how to call them, slices, right? So one should go back and find the hyperplanes that sort of separate the different structures in the three-dimensional PCA projection. But you know, that was the paper that preceded the ball mapper thing, and I was actually crazy happy when we sort of had two different approaches that are independent, right? That produce the same not the same, but sort of similar kind of morally similar kind of idea that the Jones polynomial sort of just does know about signature under some conditions, right? However strong or not, but you sort of it will be. But apart from that, I had no idea that that's what's going to happen. Again, again, we had a number of conversations with Pavel and David. Again, the separation and the concentration of knots in various clusters is like very different. So I guess I've never actually emphasized that not all clusters are created equal, right? So the bigger clusters, the size of the dot actually represents the size of the cluster. So one can sort of see that sort of the more central the nodes are, the heavier they are, and then they sort of taper off towards the ends. So again, there's like a lot there to unpack and think about. But yeah, no idea. No way that I could have predicted the thing. Yeah.
Okay, thank you. So with this, I will stop the recording. So thanks again for the wonderful talk, and then we take questions offline. And see you all next week.
Thank you.